I'm Jess McClintock, and I work on network resilience at Google Cloud. I'm here today to talk about the gaps between reviewed source code and build artifacts, and the implications this has for open source security. First, I'm going to go over a malicious package that was found on the Go module proxy earlier this year, and the strategies specific to Go that were used. I'll then go through some other case studies of supply chain attacks on open source packages, which expose the way that malicious actors can deceive traditional source level verification to insert malicious payloads into software. Then I'll discuss a model for analyzing build artifacts in terms of the capabilities that they access. And finally, I'll show how Capslock, a capability analysis tool, can be used to support source level verification to bridge the gap between source code and build artifact. So let's start by looking into how the Boltdb-go incident worked. Earlier this year, a malicious package was identified on the Go module proxy. It had persisted there for years, although it only ever had one user. To understand how this attack worked, we need to know a little more about the Go module proxy. Note that I'm going to be hand-waving over a few details here, since I'm sure this is familiar to many of you. The Go programming language differs from other package management ecosystems, like NPM or Cargo, by having the source code be the package distribution format. Rather than having a centralized package manager, the Go tool used to download the package's source code directly from a host like GitHub. These days, instead of going directly to the source code, the Go tool will by default query this Go module mirror. This fetches the relevant source code and stores an immutable copy of it, which also then serves to other Go users. This model comes with a ton of benefits, including improving the performance, immutability, and reliability of using open source Go code. To ensure the integrity of this, the Go team also runs a global checksum database, which the Go tooling uses to automatically verify that a downloaded copy of a module version is the same as what was first seen by the proxy. This solves the threat of a user somehow getting a copy of the module that has been tampered with. But as we will see, this isn't the whole story. The real Bolt package is a legitimate library which implements a simple key value store and has over 14,000 GitHub stars. In November 2021, someone made a fork of this library. The fork was called Boltdb-go, which is obviously intended to be similar to the original name, with just the Go suffix added. Soon after the fork was created, the owner of the fork published some malicious code to GitHub, tagged as version 1.3.1. This code contained a backdoor that established a connection to a remote server, allowing attackers to send and execute commands on the infected system. This version then got pulled into the Go module mirror, which would have left the mirror in a state like this. Had any Go developer tried to use the Boltdb-go version 1.3.1, they would end up downloading the malicious backdoored code from the Go module mirror. Now, this is a pretty suspicious state, and had any Go developer gone directly to the source repo at version 1.3.1, there was a chance they might notice that something dodgy was going on. So what the attacker did next was to create a clean commit, and then point that tag 1.3.1 to the clean commit. Now, if any Go developer tried to inspect the source code for 1.3.1 on GitHub, they'd see a perfectly clean repository with no malicious code. It's worth noting that there's only one other package, a cryptocurrency library, that ever depended on this malicious forked version of Boltdb. The PR to start using this fork was likely made by the attacker, who had been contributing low-quality small changes to the library for a few weeks, with no review pushback. The PR that added the dependency on the fork was big, hiding the change dependency amongst a large number of formatting changes, which were probably intended to overwhelm reviewers and decrease the chance of detection. And even if someone did inspect the payload, the relevant functions were spread across multiple files. All of these tactics were successful, and the PR was merged a few days later. Some time passes, and in August of 2022, the one package using the malicious fork actually ended up getting archived. But despite this, due to the caching of the Go module mirror, the malicious version continued to be available for only over 3 years, although it doesn't appear that anyone actually used it during this time. It wasn't until February 2025 that the package Boltdb-go was flagged as malicious, and researchers published findings disclosing this attack. This led to both the package being removed from the Go module mirror and the threat actor's repository and account being removed from GitHub. A big thing to note about the strategies used by attackers to bypass detection was that most of them focused on tricking human reviewers. This highlights the fallibility of relying on the many eyes of open source as a security mechanism. It's often assumed that open source is more secure because the code is in the open. But when there are so many ways to hide from human review, what does this mean for open source security? So now we've seen how this impacts the Go ecosystem, let's see a few similar examples that occur more broadly just to see what's possible in general. The Go ecosystem is generally considered more secure than many others, such as NPM, where new malicious packages are uploaded and identified every day. Go is definitely not alone in having unexpected edge cases that don't quite align with human expectation. So let's see how similar concepts affect the broader open source space. First, let's look at a fairly simple case of using Git versions to hide malicious changes in plain sight. EventStream is a helper package for working with streaming data, but it hadn't been in active development for a couple of years. So when a user contacted the author asking to take over maintainership of the package, the author saw it as an opportunity to shed some responsibility and handed ownership over. This unknown party targeted EventStream for a reason, but one thing of note in the EventStream exploit was that the package itself was neither the target nor was it the payload. The new maintainer added a dependency on another package, also controlled by them, called flatmapstream. This package included an encrypted payload, but that payload would only run when imported by a particular package, namely the Bitcoin wallet Copay Dash, and the payload would decrypt into a code that, of course, stole people's Bitcoin. This is an example of a classic example of a supply chain attack. The goal was modifying Copay Dash, but the attacker did so by targeting one of its dependencies. But that's not nearly the most interesting part of the attack. After releasing an infected version 3.3.6, a week later, the attacker removed the malicious dependency and published a new, clean version, 4.0.0. Why? Because of how versioning works in NPM, most projects that depend on EventStream would automatically update to the minor version change, the infected version, but they would not automatically update to the new major version. So the infected version kept on spreading, but any security researcher or diligent developer who decided to audit the package would look at the latest code on GitHub and see nothing wrong. The crime was happening in plain sight, but the evidence was hidden from anyone who looked. And in fact, this attack wasn't discovered for months, and only then, by complete accident, by a developer examining a build warning. Which brings us to our first key point. This is a fairly simple example, but we can see how the malicious new owner of the EventStream package used the discrepancy between the version shown on GitHub and the version chosen by NPM as a trivial layer for hiding the new malicious payload. This relied on tricks involving minor versus major version changes and ecosystem-specific version selection behaviors in NPM. If you don't have a solid mental model for dependency selection within a given ecosystem, it's easy to be tricked. For our second case study, I'll be looking into TJ Actions, a GitHub action that allows users to track which files have changed across branches and commits. At the time of the compromise, around 23,000 GitHub repos were using this action as part of their CI/CD workflows. The first steps in this attack took place several months before the attack on TJ Actions actually took place. In December of 2024, attackers abused a workflow in a separate repository to leak a GitHub personal access token of one of the repository's maintainers. The attacker then took no action for 3 months. It seems like they were waiting patiently for the right target to become available, because when Coinbase added a workflow dependent on TJ Actions change files, the attacker sprung quickly into action. The attacker used the personal access token they compromised from the Spotbugs maintainer as a springboard to compromise more personal access tokens until they ended up in possession of a personal access token with write permissions to TJ Actions. The attacker then used those permissions to create a malicious fork of TJ Actions and override a Git tag in the main repository to point to it. The version of the malicious fork injected a payload that dumped the CI/CD runner's memory, exposing sensitive environment variables and secrets directly into the workflow logs. Initially, this payload was set to only run when the action was being executed by a Coinbase-owned repository. And indeed, Coinbase did eventually execute the malicious version of TJ Actions change files, which leaked a token with write permissions. However, very quickly, Coinbase was alerted and the vulnerable workflow was removed. Up to this point, the attacker was very careful to remain hidden. All of their strategies had prioritized leaving as little trace or review noise as possible. But after failing to compromise Coinbase, they threw caution to the wind. They opened up the attack to all dependents of TJ Actions with the clear intent of being as visible and damaging as possible. Similar to Boltdb, This was an incident of attackers exploiting the mutability of Git tags, and additionally, the way in which GitHub handles forks. A developer might check a Git tag to determine which version of the source code to use. At this point, the tag points to a legitimate and verified commit share. But sometime later, when the CI/CD pipeline actually runs, it ends up fetching a different version of the code. This is capitalizing on the temporal gap between when a human, or even a system, verifies a tag, and when the code linked to that tag is actually retrieved and executed. I want to highlight that GitHub has recently added a feature to pin dependencies in GitHub Actions to a specific commit rather than a mutable tag. This is a vital tool for preventing this type of attack, and it should be required by default. In this attack, the use of Git tag mutability wasn't just to obfuscate. It was to point pre-existing dependencies on a particular tag to a malicious payload. Attacks like these are particularly concerning because they're so recent. Both TJ Actions and the Boltdb-go incident were uncovered this year. This shows us that Git tag manipulation is an evolving strategy, and we expect to see a lot more of it. Now, finally, let's talk about XZ, one of the most well-known open source supply chain incidents. Unlike the event stream attack, which was opportunistic, this was a long con. It began back in 2021, when a new contributor appeared on the XZ project mailing list. XZ, by the way, is a data compression utility that's fundamental to nearly every Linux distribution on the planet. There are several tricks used here that made the payload effectively invisible to reviewers. Firstly, the target OpenSSH doesn't even have a dependency on XZ. The attack depended on how certain Linux systems bundle OpenSSH with systemd, which adds the key dependency. Secondly, the payload was cleverly obfuscated as compressed test files, and due to the complex build system, it wasn't even clear that these files would be part of the build at all. This is fairly different than the other attacks that we've seen, but this attack shows us that attackers can use complex build rules and obfuscated payloads to deploy attacks. While the tests present in the source code repository, the script that unpacked them to create the backdoor was only included in the release itself. This provides us with an excellent example of how attackers can leverage the gap between source code that a human reviews and build artifact. Which leads us to takeaway number 3. The source of truth for security is the build artifact and not the source code, because the code that you build is not guaranteed to be the same code that you reviewed. While performing code review is obviously still important, and we don't want to imply that you should just let anyone check anything into every source code repo, we also need to be thoroughly examining the build artifact itself. This is the actual dependency graph for Go Kubernetes module. Even if you want to audit all of these dependencies, how do you focus limited review time on the changes and packages that are most in need of scrutiny? From source to build to deploy, there are a wide range of potential attack vectors and supply chain threats. And as we've seen, a lot of those risks are in your dependencies. Now that we've seen how many ways attackers have for deceiving human reviewers, how can we identify when our dependencies are engaging in bad behavior? The key is to perform analysis on the build artifact, what we get after we've built our source, which includes resolving and pulling in all of the open source packages that we depend on. This means that we won't just be analyzing what appears in the input to our builds, but the actual output of the builds. And this isn't a new idea. This is actually a concept that's been around for decades, before a lot of the open source software was even developed. This is a quote from Ken Thompson's 1984 Reflections on Trusting Trust, where he emphasizes the gap between source code and build artifacts. In the time since this paper was published, the trust model for developers, and particularly those who rely on open source, has only become more complicated. With the distance between the source code that you review and the build artifacts that you actually use and deploy growing ever larger. And this is where code analysis tools, and in particular, capability analysis, can come into play. We have a tool called Capslock that can help you more scalably review risky changes in your dependencies. We can think of capabilities in the familiar way that we might think of mobile phone app permissions. Once upon a time, installing an app was fraught with unknown risks. Will it have camera access or file permissions? At the end of the day, users had little choice. They could either install the app and potentially grant it an unknown number of permissions, or just not install the app. But then the model for app permissions was introduced. Essentially, this is a model for consent. Each app has to specifically request the permissions that it needs. I can see that an app is asking to see my contacts, but not asking for fine-grained location data, and I can make a decision about whether I want to install the app based on that. And even better, I have the ability to control what the app can do. I can grant it access to my location, but but only when I'm using the app. We can apply a similar model to open source software dependencies. The idea here is that each package already has an implicit set of expected capabilities baked into its functionality. Capabilities outside of that set should be avoided, and when those capabilities change, that could indicate a security issue. There are several types of capabilities that could be considered secure or privileged. Things like network access, file system access, or arbitrary code execution. Obviously, capabilities are sometimes necessary. There are many legitimate reasons for a piece of software to access the network or file system. But if these capabilities should only be happening when we expect and understand them. If I'm depending on a maths library for a square root function, I don't want it to suddenly start accessing my file system. Thinking in terms of these capabilities increases the visibility and transparency of how our dependencies behave, which makes it easier to detect possible issues and to pick well-scoped dependencies that don't use more privileges than expected. And this is where Capslock comes in. Capslock is freely available on GitHub for you to download, use, and modify for your own purposes. And it lets you identify capabilities in your package and the packages that you're importing. You can run the Capslock in the path of the package you want to analyze, or just point it to the appropriate path. And you'll get a report that includes each of the capabilities that get used and how often they're getting used. One useful thing about it is that Capslock digs into the software dependencies your package is using, including all those transitive dependencies that often cause security issues. And it does so by using call graph analysis to work out which functions your software is actually calling. If we were to only look at which packages are being imported, we would see a lot of false positives. By looking at the function call level, we can see specifically which capabilities in your dependencies will affect you. This call graph analysis identifies all paths to standard library functions, even through external packages. Capslock analyzes the abstract syntax tree that gets built by the Go toolchain, so you will see exactly what you are shipping. In particular, Capslock uses the SSA and VTA algorithms for analyzing the call graph and reports on the capabilities identified from classification of standard library functions found in these function calls. As an example, we can see that the output of using Capslock can include many capabilities, and that the ones considered particularly unsafe are highlighted. When you run the tool, you'll also get a list of all of the dependencies that were included in this analysis. And if you want more detail, you can get verbose output that includes call paths to specific capabilities. For example, here we might want to know why this package has a transitive use of system calls. And we can see from the call path that it comes from a terminal coloring library, checking to see if it's being invoked from inside a terminal environment. A key use for capability analysis is to supplement human code reviews. As we've seen from our case studies, the gap between what humans perceive in source code and what the compiler actually produces is being exploited by malicious actors. But using Capslock to analyze the build artifacts and surfacing that information to human reviewers during code review makes any change in behavior more transparent, making attacks of this kind much more difficult. When you depend on a package, you have an expectation that it has a certain behavior. If a package that you use gains new capabilities, say when you update it to a new version, this indicates that something pretty substantial has changed, since that function already did everything you wanted it to. And this intuition shows in the data. When we ran the Capslock tool over every Go package, we found that only 3% of Go package updates actually add a new capability. Because this is fairly uncommon, when it does happen, it's an event that should trigger scrutiny from reviewers. And it won't be so noisy that it adds a bunch of additional toil to those reviewers. To this end, we've created the Capslock Git diff tool, which reports on changes in capabilities between two commits of a Git repository. These commits can be specified in any way that the Git tool understands, such as branch names, tags, or hashes. For example, here we're using the tool to compare two revisions of the foo Git repository. And from the output, we can see that the new capability files has been added between revisions 1 and 2. In this case, we're flagging that this is a totally new capability, but it's worth noting that the tool also identifies new calls to existing capabilities. So even if the file's capability already existed in this repo from a different call, the tool would still bring up that there is a new call path to it. So now that we have the tools to analyze not just the source code, but the actual build artifacts and what they're capable of. And tools like this are so powerful precisely because they can't be tricked by methods like typosquatting or large PRs. Additionally, unlike vulnerability scanners that react to known issues, Capslock helps identify potential for harm by revealing unexpected changes to capabilities, even if no specific vulnerability is known yet. This shifts the security paradigm from reactive to proactive. We've also run the analysis over the majority of Go packages and made the results available on the deps.dev website. Note that this only includes packages that we're able to build with the default flags, since we need to actually build the artifact to analyze them. So now we have all these tools, let's go back to Boltdb-go. What did the Capslock results for that look like at the time of detection? Well, this is the real Bolt package, and based on the capabilities, it isn't doing anything unexpected. But when we look at the malicious typosquat, the story looks a bit different. So on the right, we have the version cached on the Go module mirror. And on the left is the version visible on GitHub. When we compare capabilities between these versions, we can see that it adds some pretty interesting new capabilities. It's fairly typical for malicious payloads like this one in this attack to execute a script and then exfiltrate information across the network. So these capabilities are exactly what we would expect to see in a malicious change. A bunch of obfuscation techniques were used to try and ensure that the injection of the malicious dependency went undetected in code review, but with code analysis, the suspicious changes would be flagged immediately. We've also started analyzing every package we can find on the Go module proxy that has modified Git tags. These are preliminary results, and we're still looking into these to identify any suspicious behavior, but so far we've seen some interesting things. Overall, we find that the majority have no capability diffs between the version in the module mirror and the version in GitHub. Of the 8.5% that have capability changes, most relate to changing dependencies or removing tests and demos that were mistakenly published. In a few cases, it seems that maintainers have also accidentally leaked private information, and it's possible that some of these users don't realize that their information is still available on the Go module mirror. As I said, this is just preliminary analysis, and while we haven't yet identified any new malicious changes, it's possible that there were some, especially amongst the packages whose source is no longer available for analysis. So in conclusion, make sure that you're pinning your software dependencies by commit, not by tag. This ensures that you aren't vulnerable to tag mutability attacks. And support human code review with code analysis tools like Capslock, which let you analyze your build artifacts to detect unexpected changes in both your software and the transitive software that you depend on. So what's next for capability analysis? Capslock was initially just implemented for Go, but we would love to see it implemented across many languages and ecosystems as possible. Excitingly, thanks to the Rust Foundation and Alpha Omega, Capslock for Rust is now in pilot, and thank you to everyone who made that happen. You can try it now. If you've got issues, or if you've got ideas about other things you would like to see in this space, please get in touch, send a PR. We would love to support you. And thank you so much for listening.